In the last video, I introduced the idea of deductive systems and how to make simple chains of inference. In this video, I'm going to introduce the deduction system we're going to use for propositional logic. And this is a variant of a system called natural deduction. So what we want to do is deduce judgments of the form P1 up to Pn proves Q. So this means from the assumptions P1 to Pn we can prove Q. And I'm going to try and demonstrate to you as we go along that the system will be sound, meaning that if we can prove P1 up to Pn proves Q, then P1 up to Pn does indeed entail Q. And we'll make sure it's sound by checking each rule as we go. And the main thing to remember here is the way we'd prove it's sound is if all the premises represent valid entailments for each rule we're going to use, then so does the conclusion. So as I said, the main judgment form is P1 up to Pn proves Q. We're also going to use another auxiliary judgment, which is that P1 up to Pn focusing on P proves Q. So this is a little bit mysterious at the moment, but we're going to come back to it later on. So this also means, in terms of semantics, that just P1 up to Pn and P entails Q, but having the focus is going to be extremely useful for organizing the proofs as we go forwards. So again, the main judgment form is P1 up to Pn proves Q, and we'll use the auxiliary judgment P1 up to Pn focusing on P and proves Q as well. Now, these lists of assumptions are going to appear over and over again, so often I'm going to have to shorten them, and the typical letter used to shorten them is gamma for historical reasons. So we're just going to shorten it to gamma, meaning P1 to Pn for some time, and I'll always make clear what the gamma is standing for whenever I use it. So let's start with the basic rules of the system. So the first rule allows us, if we focused on some formula P, then we can conclude it over here. So this says, assuming some things in gamma, so remember gamma is just some list of assumptions, and a focused assumption P, then we can conclude P. So this is basically saying, if we assume P, we can conclude P. So if we have a focused assumption P, then we can prove P. Now remember that gamma stands for a list of other assumptions. The other basic rule is how we get something into focus. So let's say we're trying to prove that some list of assumptions gamma proves Q. Now one way we could do this is by selecting one of the assumptions in gamma. So this symbol here means that P is in gamma, and focusing on that assumption. Oops. So we add it to our focus. So before we had no focus, and then we focus on it here, and then we can use that later on in the proof. So basically it's saying if we have P in our current assumptions, then we can focus on it and start using it in our proof. And this P in gamma is called what's called a side condition. It's something we check when we apply the rule, but it's not actually a judgment we have to prove, so we don't have to do any derivation tree above this. So let's see this in action with our very first proof. So what we're going to do is prove that if we assume A, then we can conclude A. So it seems obvious. Let's see how we step through this with the two rules we've got so far. So first we use this assumption. So we've got the assumption A. That's, I think here our gamma is now just the list with just A in it. And we use this assumption by putting it within the square brackets. And now, because we've used this assumption and it's in the square brackets, we can say done, and then the proof is finished. So we've got nothing above this line. So this concludes a proof that A proves A. And now, for these two rules, we have to think about soundness. So done is sound, because what we're doing is assuming P, and we know that if we assume P, then it entails P, no matter what else is in gamma. So the extra assumptions make no difference. So this means that gamma, comma P entails P. And for use, then what we're really doing is we're just taking one of the assumptions out of gamma. So P has to be in gamma, and then we're just assuming it twice. So it's okay. And what we're doing is saying, oh, well, if we can prove Q assuming P twice, then we can prove Q assuming P once. So it's okay to assume it once. Now, This is all very well, but all it allows us is to prove things we immediately have in our list of assumptions. So we don't get any more than kind of bureaucratic logic where we can only prove things we know to be true. So in natural deduction, we also want to have rules for the connectives, so things like and, or, implies, and not. And the rules for connectives come in two different kinds. We have introduction rules, which show us how to construct a proof with this connective. So we want to prove something like A and B. And then we also have elimination rules, which show us how to use an assumption with some connective. So if we're assuming A and B, then how do we use this? And to help you remember this, here's a very rough analogy, but it can be made quite precise. Introduction rules are a bit like constructors for building objects. And elimination rules are a bit like methods for taking apart objects. And we'll see this now by looking at the rules for AND. So here's the rule for AND introduction, which is called split. So the idea is to read this bottom up. If we've got a list of assumptions gamma, and we want to prove Q1 and Q2, then we can do this by proving Q1 and Q2 separately. So we want to prove this big formula Q1 and Q2, and we do it by splitting into Q1 and Q2, and we prove those separately. So to prove P1 and P2, we have to prove P1 and P2. This rule is sometimes called AND introduction, because it's the rule that, reading top to bottom, introduces AND into the proof, the AND symbol. So here's an example proof. If we assume A and B, then we can prove a logical symbol and B. And the way we do this is, well, we're proving A and B, so we do a split. So we get two subproofs here. And now we have to prove A from the assumptions A and B, and we have to prove B from the assumptions A and B. And now both of these, we do what we did before, we use an assumption. So to prove A, we're going to use the A assumption here, so we put it in square brackets, and we keep a copy of it over here because it's still an assumption we can use later on as well. And then we say done, because the thing we're proving is the thing we have in brackets. And similarly over the other side, we have put the B into square brackets by the use rule, reading up, and then we say done to do the B. So to prove A and B, we split into proofs of A and B. In each case, we use the corresponding assumption, and then we are done. Now that shows us how to prove things which end in A and B, but how do we use an assumption which is an AND? So let's try AND elimination. Sorry, this is called AND elimination. So this is our first example where we manipulate something which is in the focus. So let's look at this, the first rule first. Let's say we're focused on an assumption that P1 and P2 is true. Now we can use the first rule to then change this assumption to just it's P1 is true. So what we're saying is, if we can prove Q from the assumption P1, then we can also show it from the assumption that P1 and P2 are true. And similarly over here, if we can prove Q from the assumption that P2 is true, then we can prove it from the assumption that P1 and P2 are true. Or reading up, we can say, well, if we've got P1 and P2, then we call a method just to get the second part in this one, or we call a method and get the first part in this one. So, in other words, if we're focused on a formula P1 and P2, we can select either the first or second component to focus on. So let's see how this works in another proof. So let's say we're assuming A and B, and we want to prove B. So first, we focus on the assumption. So we focus on A and B. And then we use the second rule. So we've got the focus A and B, and we're going to take out the second part B, to get B in the focus. And then we can say done, because the thing in the focus is the thing we're trying to prove. So this proves that A and B proves B. Now, we can think of true as a kind of AND with no components. So it's a bit like a nullary AND. So to prove true, we don't have to do anything. True is always true. So this rule is an axiom saying that true is always true. So true is always provable. And to eliminate true, well, there's no elimination rule, because there's no information we can get out of true. So for an AND, we can get out that one of its sides is true. For true, there's no information we can get out of it. So in summary, the judgment forms for focused natural deduction are P1 up to Pn proves Q, and then at some parts in the proof we have a focused part which allows us to use one of our assumptions to prove Q, and we can manipulate it, as we saw with the AND rules, with the first and second rules. And we've seen the rules for use and done, which allow us to, for use, move something from the assumptions into the focus, and done, which is when the focus is the same as conclusion, we can say that branch of the proof is finished. And we've seen the rules for introducing and eliminating ANDs.